guys. So today we will be doing the second day of the LLM crash course. I hope you have had a beautiful and enjoyable journey in this series of deep learning. And I hope today you are more matured enough intuitively to understand the day two. And I also hope that the day one makes more sense after learning the deep learning. One part of the day one was left, that is the deep learning process that we will be starting with today. Moving on to the data preprocessing, experimental setup, and the GPT architecture. Today's goal is to show you that how to build a small LLM from scratch and give you the necessary knowledge so that you can also do it too. Before I begin, I want a confirmation that all of you have learned what is deep learning over the past few days, the weeks. Can you say an yes in the comment box or raise your hands? So as I said, I will be starting with the initial exposition of what is deep learning in this specific setup. So all of you are good with knowing what is deep learning in details over the last few weeks. Did you understand? Any questions? Okay. I assume yes. So as I said, I will be starting with starting with a very brief swift crash course on deep learning, and I will move on to the LLM part of it, where you train deep learning with language data. So for revising or connecting back to the first day, as we have seen that language is nothing but a tensor. Okay. And in deep learning, there is something called input X, which is a tensor, and an output Y, as you can see on the screen. And the output Y is kind of the actual what it should be, but it always doesn't happen. So we have an approximate Y hat, which is nothing but a function of the input. Now this input, this function, which is a neural network, has some unknown parameters theta, unknown knobs, let's say. Now, as you change the knobs, the prediction changes. So the whole idea of deep learning, so the idea of deep comes from the very fact that the function has a deep hierarchical structure. And that is nothing but something called layers that like it moves into the second layer, third layer. So that is the hierarchical structure, what I mean. Deep hierarchical structure. This is motivated by the how information flows through our brain. Okay. That is where the deep aspect is coming. And the learning aspect is coming from the fact that we are using data to estimate those best values of the knobs, those parameters theta. Okay. So deep comes from the deep hierarchical structure, and the learning comes from the fact that we need to find those best parameter knob values, which gives the best output, Y hat. Now, how do you find that? We want this output Y hat to be as close as possible to the original Y. Okay. So there is naturally a loss defined over that. So we have an input Xi. So now we have multiple data points. This was just for one data point, this slide. Now we have multiple data points, X1, Y1, X2, Y2. x3, y3, dot, dot, xn, yn for n data points. So for each data point, we calculate a loss between this is the y hat I, f of xi, that the predicted one, and the original true value. Okay. And we calculate the loss, the difference, how close this is. This, we want this loss to be as minimal as possible, right? We want this difference to be as minimal as possible, as small as possible. So we want it to be over all the parameter, all the data points. So we sum over all the losses, take the average kind of thing, you can say mean. And we want to finally minimize this loss, which is nothing but the average loss for all the data point predictions. And this loss is invariably a function of theta. As you can see, this loss is invariably a function of theta, because which we don't know. So we have now a minimization problem where we minimize this loss. So you can imagine this loss is kind of this, very simplified way. This loss is a function of theta, so the loss will be something, a curve like this. And we want to find that perfect theta hat which minimizes the loss. The loss will never be zero, but loss will be minimum. The loss will never be zero because we do not even want it to be zero because of something called overfitting. Okay. We do not want it to be zero. We want it to be minimal. So this is very important. This is how we find the best possible theta, and hence the best possible function, because once you fix those thetas, the function is fixed, right? So this is the basic deep learning mathematics, simple basic deep learning mathematics. Now, the main mathematics of deep learning comes from, so there are two parts of deep learning. There's a mathematical part and there's an engineering part. Okay. The main mathematics of deep learning comes from the fact this F is designed to be very different for different data points. For example, you must have learned about images. For images, we have something called convolution. We have seen last day for language or for sequential data, we have transformers. Okay. Or we also have recurrent neural networks, RNN or LSTM based. Right? So there are many different types. If you go to networks, network data, social media data, network data, you will have graphical neural networks, GNN. And there are many different types of data for various data structures. But that is a level of different level of mathematics that we also need to know. The two level, as I said, the deep hierarchical structure, the mathematical structure, the deep hierarchical network, and the learning process. But the learning process is very simple, as you can see. We have a loss function, and it is minimized, and the best theta hat is found. Okay, so this is very simple, very simple. But there's another layer of engineering. The engineering, I will come to that soon. So I will come to this slide soon, but let me talk about a bit about gradient descent. So any questions till this point of time, guys? Did you understand this first two slides? Any questions I can help you out with? All good? Yeah, feel free to ask questions if you have any, because you already know me. At least you have done one class. I will not ask you like name by name. That will not be a proper use of time for today. Okay, I assume all of you have understood. Please ask me doubts if you want to. Okay. Thank you, Rupali, for saying yes. So now the next natural question, just a bit of revision, is how is this theta found out? Okay, how is this base theta found out? In a numerical analysis way, in a computational way, the answer is simple, called gradient descent. The gradient descent is simple, that you have a starting point and you slowly move towards the minimum, one step at a time. So let me write down the equation theta hat k plus 1. This is, so every theta k, so we find out theta 1, theta 2, dot, 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 theta n, and we, as we increase n, it ideally should go towards that theta hat. Okay. So what do? we find an iterative algorithm. That was the way to do optimization before deep learning era also. Iterative algorithm. So what we do, we start simple. It's like going down the hill. So we start at a point in the hill and we take one step towards in the opposite direction of the gradient. Okay. So here it is a positive gradient, as you can see. So we go towards negative direction. Okay. So we have theta k. This is the old one. This is the new one. And what we do is we go towards this is a step size. That is, so imagine you walking down the hill of a valley, not a hill, a valley between two hills, and you're walking down to the lowest point of the valley. So what you do, you walk down the valley, and let's say you are walking, so you have a step size. So this is a step size. And you have a direction. So when you move towards, there's a direction and there is a step size. So the direction is given by the gradient, by the negative of the gradient. Gradient is nothing but the derivative of it. Okay, derivative of the function at that point. If it's steep, you go down quickly. If it's not steep, you go down slowly. So that's how you define the steps, right? And this happens at theta k. So this is how the gradient happens. Now, there's an engineering aspect toward it. Let's say you have millions and billions of data points. This will, for just one iteration, it will take a lot of time. So there are methods like mini batch gradient descent, where we like stochastic gradient descent, when we randomly take 1 point. Or we also have mini batch stochastic gradient descent, where we randomly take a few points in a batch and then average it out. But mathematically, on average, as you do it for a longer time, longer epochs, to be very precise, it is been shown mathematically that it is convergent to the same minimum, same theta hat that the batch gradient descent does. Okay, the reason is very simple, because the average of, let's say you have a let's assume that you have a population. Let's imagine you have a population, and from that population, you can find the entire population minimum, let's say, of their heights. You can find it, but you can also find it like you can take a subpopulation, a sample of the population, find its mean, and then subpopulation find its mean, and then take its mean, like this, right? So on average, it also boils down to the same thing. That's what stochastic mini batch gradient descent is. So these are some engineering techniques, rather I would call numerical analysis techniques, that are adopted in real life so that the optimization is done in the same exact proper manner. So this is how the theta hat is done. Now let's me talk about a bit about the engineering, because this is also will help us in coding, understanding the code. So this is the general, these two images have been made by me. So these are two general ways to engineer or code any neural network, okay, for whatever thing you do. So of course, a neural network is an input and output. I represent that as xi comma yi. Okay, you may say that in unsupervised algorithms, what is the yi? That's a very good question. Or in autoencoders, I don't know. Did you guys learn about autoencoders? Yes, no. Okay. So if you have learned about autoencoders, you may ask, can you tell me what is the output? What was the output of an autoencoder or encoder decoder structure, let's say? Can someone tell me? So input is xi. What is the output? What is the any ideas?
So the output will be a reduced hyperspace of the input variables, where the input variables get combined. So if there are say 10,
I am talking about, that's an autoencoder you're saying. Let's say there is a decoder too. Then?
Oh, the decoder output should be equal to the input.
Exactly, very good. So what will be the yi there?
Xi.
Very
will
good,
be
super.
equal to xi.
So it's xi comma xi. But essentially what I mean is that there is something called xi and there is something, so essentially it's xi hat, you can say, kind of. In this case, it's yi hat, you can say. But what I'm saying is that there's this concept of input and there's a concept of output. Okay. So this is what I'm saying. This is very important to understand. So very good, Rupali. I hope all of you understood Rupali's answer in autoencoder decoder. So in xi, there is something like this where we do a basic x star I, let's say, and from that we have an x hat I, and we want to minimize the loss between xi and xi hat. Okay, so always there will not be yi specifically. You actually design the yi based on the problem. Very good, Rupali. So now let's understand this very carefully. So we have a raw data. Okay, let's take the language example. So let's say you want to do, let's do a thought experiment. Okay, let's say you want to build, let's say how GPT is built. GPT is, let's say, built using web data, right? So let's say the raw data is the web Wikipedia pages, right? That's a raw data, for example. Now you want to organize all the, now you download all the, let's say there are 100 Wikipedia pages, okay, for example. So imagine you have 100 Wikipedia pages, they are HTML files, let's say. You download them as HTML files. Okay. And then you do some pre-processing to change HTML files into, let's say, TXT files. Okay. Let's say HTML to TXT. I'm just giving an example. And that's also in terms of, okay, you can say TXT. Now let's say you have 100 TXT files and you combine all of them into a single TXT file. That's your data, let's say. You organized all the files into a single TXT file. And actually, this is the most important step, I would say. For example, in my research, in my PhD, let's say the doctors take images of patients, right? Or the doctors give me their radiology reports in language format. Now that is very unorganized. That is in their data, because all these are saved in some software and the softwares have different ways of download. So there are different files, data structures in which they are saved. Now I have to combine them into something that the machine understands really well. Let's say TXT, okay? Or I organize them properly, because each image or each patient is a different name. So you have this data organization is very important because this is going to stay for a long time. I have to spend my entire initial days in data organization. And then we do some pre-processing. In pre-processing, in my case, in imaging case, the pre-processing can be, let's say, I want to reshape an image into a square, okay, because it's easy to understand. Or let's say, in a square, okay. Or there are many very different ways of doing pre-processing. In language, probably you will see what we do in data pre-processing. You will see what is pre-processing. When you have to change in vocabulary, build all the tokens, all the tokenizing aspect is pre-processing, okay. And then we have to build something called xi, yi. What is the input? What is the output? What is the input? What is the output for all I? And that's where the dataset class is built. That's the dataset class, where the dataset class, essentially the output of the dataset class is nothing but, when we build a class in Python, that's what I'm saying, class dataset. When you build the Python and you take the dataset module from the NN, neural networks Python library, that's what you're doing. Essentially, it's changing you're doing some pre-processing, you're taking the raw organized files and you're outputting them into xi, yi. This step is nothing but done by the dataset class. Now, after this, you build the entire dataset. You have something in the dataset class, you have something called indices. You have something the length. Naturally, they have a length, right? Let's say their length of data is n. Now, this depends. If it's image and label, let's say image, you're doing a prediction of cat and dogs. And you have n images and n labels. So the dataset class is n. But in language, it's a bit different. In finance, stock market prediction, it's a bit different. It's varies from problem to problem. So that's what you do in the dataset class. From dataset class, you have something called the length of the entire dataset. Now what you do is divide that length into three sections. One is training, one is validation, one is test. We have already learned about this surely. In training, you train the model. In validation, you tune the hyperparameters, and you test. You essentially see that how the tuned hyperparameter model actually works and report that on the test data. That's what you do in the dataset train, test, and val split. Now you do it on the indices, because all datasets is an index of 1, 2, 3, 4, 5, and you have 100, let's say, and you build it up into these 3 indices. And from those indices, all the xi and yi are captured. Understand that xi and yi can also be a matrix, a graph, or a single numerical float value, a single one-dimensional or multi-dimensional. That's the whole part. I believe this is the most important part of the dataset class. This and the I will come again. This too, because all these things, all the other things you can. These are all inbuilt, but these two things, the red part, model part, and the dataset class part, is something that is very specific to your model. So this is something you have to design yourself. Other things ChatGPT can help you. Okay, so after you got the indices, then comes the batches. As I said, the batches is nothing but I will come to this again here. So I probably should have kept this earlier. So I will again repeat once again. So data directory, where the dataset is, we save it into files format, and then the dataset class. There's a bit of more information here. As I said, we have the tensor of x1, x2. So these are the features, and the tensor of y. And we have these 3 functions. The length function gives you the roll number of dataset. The get item functions gives you the output of xi, yi. Okay, there are other functions too for pre-processing, as I said. And the output, as I said, is nothing but xi, yi, let's say. Okay, now there is a train test split, as we have said. And then based on this, the data loader is loaded. So what is the job of the data loader? The job of the data loader is nothing but dividing, let's say, the 100, let's say whatever the length of the data set, into specific parts. Because if there, let's say, millions of data set, it cannot be done in a single gradient descent. Like the computer cannot load it. So what they do is that they divide into batches, and then they do it on each of those batches. Then they feed the model, update the gradients just on those batches. Okay, this is an engineering aspect, and it has been shown mathematically. It converges to the same thing. We have already talked about it here, right? Here again, this should also go before probably. Yeah. So those batches are being created by this data loader class, function. Okay. So this individual data loader. So we build one data loader for training, one data loader for testing, one data loader for validation. So all of this are dividing those data set into these batches. Now we are building this model class, which is nothing but taking the input of X and giving the output of Y hat. Okay. And this is something you define another whole class of the model. In GPT, it's just thing with the GPT architecture. So in whatever AI thing you do, the most important 2 things are dataset class, and the model, which are different from place to place. Other things are all fixed mostly, unless you are doing something very different. And then the basic idea is, you can see here, there is this yi hat that you are predicting. Then there's the loss, then there's gradient update, and there's a y hat. Now this is happening for each batch, and one epoch is nothing but, so understand this very carefully. So each batch data is like this, because from all the data tensors, let's say it's n cross c cross h cross w, it is divided into these batches. Let's say n equal to 100 and batch size equal to 20. So there are 5 batches. The entire data set is divided into 5 batches. So this train data loader is divided into B batches. Similarly, validation data loader is divided into some B batches. The B may not be the same. This is for just for illustration purpose, but the entire data set is divided into B batches. Okay, all the data loaders. Okay, did you understand till this point of time, guys? This is very important to understand. All of you understood this? Okay, thank you, Indol. What about others? Okay, thanks, Rupali. Thanks, Konishko. Any questions? Thanks, Lucky. Okay. So I hope, thanks, Shurajit. So I hope all of you have understood this. Since you have no questions, please feel free to stop me and ask questions, okay? So to repeat, we have this data directory. We build this dataset class, which is nothing but data pre-processing and changing into xi, yi format. And then we get the train test validation indices, out of which we created these individual data loaders. So this individual data loaders is nothing but giving these B batches 5 times. Okay, and it's a for loop. It's just a enumerate. It's a for loop. It's a list, and each list element is a batch, set of batches, like batches of those, and that's what it happens. That's what is happening. And then there is a loop inside for all the batches, 5 batches, let's say. So there is a batch size is B. So number of batch is, let's say, 5. So it's happening for, so each training batch, the gradient is updated. Taking those, there is some code data, the theta is updated. So how is the theta updated? So this, for each training batch, the model takes in the X, it calculates the loss, it minimizes the loss using gradient descent, and then the model theta hat is updated, and the model is also updated because the theta hat is also updated, right? And this happens for 5 of them. And once this 5 is complete, we call that one epoch has been completed. Okay. And this happens for, let's say, thousands of epochs, or 200 of epochs, or 50, whatever the epoch number is. And this happens for all the epochs. And when it happens for all the epochs, whatever you decide, we say the model, this is the final model, we save the model. Okay. So we loop it over all the epochs till convergence. Often the convergence is early stopping, where the training and the validation loss, the training loss will always decrease, okay? Because the model is trying to interpolate, like make it the loss 0 as much as possible. And it can do that, to be very honest. But at certain point of time, the validation loss will go up, will increase. And that's point where it goes up, that's where we split, that's where we stop training, and then we take that as that's called early stopping. That takes it as the best model. And then we use that model to validate or to do the testing or validation, essentially. And we save that model somewhere. We save that model in a PTH file, as you can see, and then we do testing or evaluation, which is nothing but using those same data loaders. So instead of training, we will just pass through it. Okay. So there will be no loss calculation or minimization calculation. We will just see that for the specific testing purposes, we will see that what is just the output, okay, and what is the original output, and then see the difference, and then we see, okay, this is the accuracy. Okay, so this is how the entire deep learning process and workflow is. Okay, the most important part is again the dataset and the model class model. This is the most important aspect that you need to understand, you need to remember, and that's where innovation comes. Okay, all of you understood this, guys? All of you understood the entire deep learning process. Now we will slowly move into how this whole process is applied for LLM, for large language models. All of you understood this? Yes or no? Can you say yes in the comment box, because this is one module is complete. I will now call out your names. Angana, Orijit, Borshon, Gargi, Hindol, Kolpita, Kanishko, Lucky, Mrityunjoy, Pooja, Rohini, Rupali, Rutuparna, Saurabh, Sritama, Surojit, Shushmita, Swapnomoy, and Riti. Okay, good. So now, any questions I can help you out with? I hope it was a... decent revision of the concept that you have learned. Now we will use this whole strategy. As I said, the two important aspects are the dataset class and the model class, and that's what we will understand now. That how for a large language model, a data set is transformed, is pre-processed into those xi and yi. That's number one. And how the GPT architecture is working. What is the mathematics? What is the mathematics behind it? These are the only two most important aspects. Rest is everything is same. So the first question is that let's assume one thing. So I took the Wikipedia page of Satyajit Ray, which is a text, and if this is the data, what is the xi and yi? What is the x and y? That is the main question. Before we feed it into the neural networks, also we have one. So the first question is that what is x and y? The next question is how to train and how to infer. We have already discussed about this, how to train and how to infer, but it also asks that the model. But I will be explaining the entire thing before I have discussed in terms of LLM now with the codes. So the first thing is dividing the data into train and test. So I think this is repeated 2 times. This slide is repeated 2 times. So I will delete one. Okay. So the first thing is how to changing the data set into train and text. What is the x and y? It's simple. So we do it something called using tokenizer. Okay. We have also discussed tokenizer. It's nothing but the embedding. But tokenizer is essentially nothing but it takes the data, divides it into tokens, and give them embeddings, or just the tokens. Let's say the tokens. Okay. Now, in our previous discussion in day 1, we have said that words can be a good example, characters can be a good example. But GPT do it in some other ways, byte by byte pair encoding. Okay. And you can see we don't know what it does, but essentially what it does, you can watch Andre Karpathy's video. I have shared his video. He's a 1-2 hour tutorial on tokenizer. But essentially there's an algorithm, byte by byte algorithm, byte pair algorithm, which essentially sees that which tokens have occurred multiple times together, and then getting them together and doing this over iterations and iterations to find out the best tokens. Okay, so it's a very hard algorithm, it's a very simple algorithm, but that's how GPT does. But you can imagine as it words or characters. Recently, Meta has done one thing which is each byte wise. So ideally, it should be, if it's byte-wise, that makes more sense. But yeah, that's the whole idea. Okay. So essentially, tokenizer is nothing but dividing this entire text into these tokens. Okay. So a text is now divided into a set of tokens, which is, let's say, x1, x2, ... xn. So this is the most important part to understand. Okay, a text is divided into these tokens x1, x2, x3, xn. The entire text is divided into tokens. Now these are called by indices. This 1, 2, 3, 4 n are indices. Okay, so let's take an example. Okay, we will anyway look into the example later on. Let's say, but I'm trying to find one specific. Yeah. Let's see if I can find a repetition. No, I cannot find a repetition. Let's say there should be a lot of his surely in this. Find out if you get any his. Okay, his is there. So what I'm saying is that this individual tokens which repeats again and again has this IDs. Okay, so imagine the entire text is broken up into pieces. Okay, let's say there are 1,000 pieces. That is called a vocabulary. Okay, now those are 1,000 unique pieces. There's an entire text has probably 1,000 unique pieces. So so any text is nothing but a permutation and combination of those pieces, right? So those pieces are saved in the memory. So instead of calling those specific pieces, what I'm saying is that a text is nothing but those indices. Let's say this is 1, this is 101, this is 205, this is 6, dot, dot, dot. So a text is nothing but a sequence of indices of tokens. Now there are various algorithms, as I said, so tokens is nothing but a way, tokenizer is nothing but a way to divide into tokens or pieces, which make sense in some way. Like it doesn't make sense to randomly do it into pieces, right? So which has some inner meaning. The same thing is actually done on images. So I don't know if you have done vision transformers, guys. Did you do vision transformers? Did anyone teach you vision transformers? Okay. So in vision transformers, what is done, these tokens are something different. There's an image, let's say an image is this is 1, 2, 3, 4, 5, 1, 2, 3. So it's a 5x5 image. Each one is a pixel. Okay. So what is done is each one of them is a token. Each pixel is a token, or each, let's say, it's not a pixel. As far as I remember, it was 16x16. It's square. So each square, which is a small patch of the image, is a token. Okay, this is how it's now. It has indices like 1, 2, 3, 4. So it has indices, and we call those indices. So in images, it's like this. In text, it is like this. You can similarly build different ways, but there is a specific way which works by a lot of experimentations we have seen. Okay, so now every slide I will ask you whether you understood or not, because there are different concepts that we have not discussed before. So all of you understood this tokenizer thing, guys? Yes? Can you give a thumbs up or say yes in the comment box? Okay, good. Any questions? No. Okay, so now dividing the whole thing into training and test again. Now let's understand this. So these are, let's say, sequence of 4 tokens. So let's say in this case, we have seen viewing, let's say these are tokens, and these tokens are nothing but this. As I said, we do not call the tokens by those values. We call the tokens by those indices. So this is 868 is the roll number of the tokens in the entire vocabulary. Okay. So they are fixed vocabulary, and those are fixed. Those are those tokens from those vocabularies. So let's say these are 4 tokens. This is x1, x2, x3, x4. And using a neural network, we predict what will be the next one, x5. That's the problem now. Okay. So using a neural network, we predict what will be the next token. So the input is x1 or xn, and the output is the yi. This is the x, and the y is nothing but xn plus 1 hat. What will be the next token? So how to do it? It's simple. We do not actually do xn hat plus. What we do is we find over the 1,000 vocabulary elements what is the probability. So instead of predicting xn hat, what we predict is, so let's do some math. So the input is this x1 x dot xn, and let's say the vocabulary is v1, we did over v 1000, which we don't know. These are fixed. That's why I kept 1000. Let's say it can be like some vk, capital K. So what we do is that we have this, and this is the function x comma theta, and the output is not xn hat plus. The output is the probability distribution over this vocabulary tokens. Okay, these are vocabulary tokens. And these are input tokens. So this will be a probability distribution. So output is therefore a 1000-dimensional tensor. So which first one says probability xn plus 1 is probability next, let's call it next. Probability next is equal to V1. Probability next is equal to V2. This probability distribution. Okay. So you can ask this simple question, that how does the model make sure these probabilities are corresponding to the same VIs? Does anyone know the answer? How does the model make sure that these are the relevant probabilities of the same vocabularies? Anyone knows the answer? Any idea? How does the output of the model make sure that these are the predicted probabilities of the VIs? Why doesn't the model get confused? Any idea? You know the answer, you have been taught this. How does the model know that each one of them is a corresponding probability? Yeah. No idea? Any guesses? Some wild guesses? You have been learning this for quite a few months. Now, as I said, I want you to tell me the answer. Anyone? Any guesses, guys? Angana, Borshon, Gargi, Hindol, Kulpita, Konishko, Lucky, Mrityunjoy, Rohini, Rupoli, Rutuparna, Saurabh, Sritama, Shupro, Surojit, Shushmita, Swapnamoy, and Riti. Any idea? How does the model make sure? Let's forget about large language model. How does the model make sure that the output is what we want? Okay. So the answer is very simple. The answer is we train that way. So when we are training probability, we make sure that the data has those exact probability, like in case it will be 1, 0, 0 if it's V1, okay? And then their difference is taken. So that's where the data preprocessing is very important. So we arrange those data into this specific XI and YI format. Okay. So in this case, the vocabulary, let's say it's like this: A, B, A, C. Okay. And the original text is this. Let me tell you how it happens. And let's say the vocabulary is therefore A, B, C, D, right? And this is the original text. This is the text, training text, and this is the vocabulary, right? Now let's say you predict every 3 of them. So this is the input. This is one data point. This is the second data point. B, A, C, and then D. Okay, so there are 2 data points out of this entire text, and this is the vocabulary. Okay, so how is it training? How is the data preprocessing happens? It's simple. So this index is 1, 2, 3, 4. So this is represented as, understand this very carefully, 1, 2, 1, and C is 3. And this is represented as 2, 1, 3, and then 4. Okay. So what is happening? The data preprocessing, the data set class is outputting this. So xi, x1 is this, and y1 is this. X2 is this, and y2 is this. So when y2 is this, you see the function model is predicting what? Understand, this is where the whole thing comes. It becomes very important. So this So, okay. So let's take this blank page and let's copy this and paste it here. So this is what the input and output is. So now how is the x? The x is the same. So x is indices because once the indices are given, it can catch from the vocabulary. So let's say the input is coming like this, 1 to 1. There's this function going. This is a neural network. Let's say f of x comma theta. What is the output then? That's the main thing. The output is, since it's a probability distribution, the output is over the vocabulary. Remember the vocabulary here. So it's 1, 2, 3, 4, right? So vocabulary is 1, 2, 3, 4. So it's a probability distribution over that. So it output 4 numbers. Let me write it like this. It outputs probability of V1, probability of 2, probability of 3, and probability of 4. This is the probability over vocabulary predicted. And what will be the actual one? Tell me. Can someone tell me what will be the actual one for x1? This is y1. And what will be the actual one for x2? We know y is equal to 3. So what will be here? Here it cannot be 3. Or what will it be? Can someone tell me?
So something like 0, 0, 1, 0.
Very good.
0, 0, 1, 0.
Very good. Thank you, guys. Exactly. So it will be, first case here it is y2 is equal to 4. So here it will be 0, 0, 0, 1, and in this case 0, 0, 1, 0. Essentially we have 1 in the third place because output is third, and we have 0 in the other places. This is called one-hot encoding. Okay. This makes sure the predicted output is what we want. Right? Now the probability will now move towards 1 more and others towards 0 because we are minimizing the loss. And that's how it learns that after this 3, this comes up. So this is essentially the basic mathematics of how the data set is divided into train and xi and yi. That's the data set class, and also the one-hot encoding and how the loss function is. So now between this you can make sure a cross entropy loss, let's say, because it's between a distribution between probabilities. All of you understood this carefully. This is actually the most important aspect of dataset distribution, like how the xi and yi are arranged. Did you understand this, guys? Yes or no? All of you understood this? Thumbs up, yes, no. Okay, this is very important, guys. That's why I want your answer. Okay. Any questions? Okay. Very good. Now the next one. So what is this whole expression? We have already talked about this. This GPT architecture is nothing but this giant mathematical expression, as I said, f of x comma theta. This theta are these knobs that you have to update to get this. In this case, the slide from where I have taken this, this is the vocabulary numbers. This is the number of elements in the vocabulary, 10,000. Essentially, they are usually 100,000 tokens. 10 to the power 1, 2, 3, 4, 5. 10 to the power 5 tokens in a vocabulary. So among all the text, all can be divided into this 10 to the power 5 tokens. So essentially, a vocabulary is this, and when you are including this, this elements of which token index you are taking. Okay, and yeah, so that's the entire idea. So we have this output is this probability of those 10 to the power 5 over this probability distribution over those 10 to 5 numbers. Okay, that's the output. Okay, so now how inference is done? This is very important, guys. So let's say we input 1 and the output is 860. Let's say input is 1, output is 860. Okay. So here I have fixed this 3, but this can be varied. This can be have an upper hand. Okay. So you can say it's 0, 0, 0 like this. So when you input 0, 0, 0, 91, that is, you can say something like empty, like here. That's an index in itself, let's say. And when you say 91, and you input into network, it gives that the best possible, essentially it gives output of probabilities. This is the probabilities. And the best possible output is 860. You can take the max. Okay. Often what can happen is that if there are multiple of similar probability, you can sample from, let's say it says that after a 91, the best possible top 5 are this, and you can take top 5 and then sample from them randomly. Okay. You can say these are the top 5 and sample from them randomly. This can increase your creativity. Okay. So I am boy and girl and man, woman, or a human, any noun or form of human is more probable than an animal or an inanimate object, right? Because animal, it's hardly, there are less. Yes, there are stories where you can actually say an autobiography of an animal, then the animal can say in first hand, but usually it's a human because that's human data. So you do not just always want the top, because the top can be many things like man, woman, boy, girl. Okay. So you can actually randomly sample from it, because every single time, therefore, GPT can give different outputs. Okay. And that's why the creativity comes up, because human beings think differently, and that's how creativity is. Many things are output is possible. You just select randomly one of them. That's why sample is written. Now, once you select that and you append it to 91,860, so you append it to 91, then you generate, then you input that into the model, trained model, and output the next best possible token, 287, and then you input it, and then you output the next best possible token. So essentially what you predict, you input it into the model. I input it into the next prediction output. Okay, that's how the inference is done. That's why it's generative AI. That's how you're generating. Okay, that's how you're generating. All of you understood this, guys? This inference is very important also. Yes, no, questions? Okay. It's very important again. Okay. Any questions? No. Okay, good. Now this GPT model. Now this GPT model is it's a detailed model. We already understood what it is doing, right? We already understood transformers. We understood the attention, which is, so if you do attention multiple times, you get a transformer. Okay, layer. And you do it multiple times, because as you do more, so we already talked about position and encoding last day. We have input. This input is transformed into these tokens, token IDs. Those token IDs are transformed into embeddings. And we always have those token IDs as a positional encoding, and we add those embeddings. Okay. And then we run through this transformer blocks. This transformer blocks is nothing but attentions. This attention are nothing but looking into each one of these relationships one by one. In the first layer, there is one by one relationship. In the second layer, as I think someone said last time, I forgot, the receptive field of the relationship increases. Okay. And then they layer normalization. These are like basic deep learning stuff. And then we get the output. Okay. Output is nothing but the probabilities. Now this transformer block is nothing but this layer normalization, multi-attention, all these things are done essentially to increase the relationship and whatever worked for them. Okay. So these are mathematical structures. You have to understand what is simple. For example, dropout importance is nothing but so that it forgets a few of the blocks. Like for example, I believe, like if you do the experiment with your own mind. Let's say you do something for, let's say you learn about large language models for 2-3 weeks straight. Okay. And you do not do it for a few days again or a week, and then you come back. So in this time, when you do not do that, you know what happens? In that time, the less important neurons are deleted. Okay, the less important neurons are deleted, which are occurring less number of times, or the memory is erased from those neurons, even in the brain. And again, when you learn it again, the most important ones are again learned. So these dropout are essentially ways of relieving those unimportant things and showing more focus on the important things step by step. So that's what the use of dropout. And all these things are done either for engineering or for better learning purpose, any one of them. For example, layer normalization is done for better learning purpose because it has been shown that with this there is better learning. So there are many things. You should read the book Understanding Deep Learning. You will understand this mechanics of neural networks, where it has been shown that, like, why did RNN didn't work for language? Because of our LSTM. Because what happens is that there is something called vanishing gradient. There's so many logistic blocks out there in the LSTM. So let's say you have an input, there's a logistic block. What does a logistic block do? It changes between 0 and 1. So if you have 100 of these logistic blocks, you have some number which is between 0 and 1 to the power 100 or 1000. Essentially, it goes to 0. So the gradient goes to 0, and this is called vanishing gradient. And you end up learning nothing. Similarly, this is called exploding gradient. When there is a certain transformation, unlike logistic, like tan h or something like, not tan h, but there's similar such operations which makes the number more than 1. So if you have a number more than 1 and it is multiplied 1000 times, it goes to infinity. So that it's called exploding gradient problem. To solve both these problems, there are many things. One is ReLU block is done, ReLU activation is kept instead of logistic. Okay, because ReLU activation, you can see it's x. If x is greater than 0, so x can be more than 1 and less than 1 both. So it keeps what it is. So that is an useful block for not normalizing, so that the output is not between 0 and 1. Similarly, batch normalization, layer normalization, all these techniques, so that this vanishing gradient and exploding gradient problem doesn't happen. Okay, the other things too, the residual, the skip connections added. Skip connections are added in ResNet and many other, all of them actually nowadays, so that it doesn't forget the previous, because every layer the information is transformed, right? And as the information is transformed, you should also remember what was the actual one. It's constantly added, constantly added. That is what skip connection is done. Otherwise, it will forget what's in the past. So these are few engineering techniques that are built to make sure the model is learning properly. Okay. So now let's come to the coding part. Okay, all of you are good with this, guys. I hope. Let's move on to the next part. So as I said, data preprocessing part. So understand what is being done in this code. First, we have this ray.txt file, okay, where the entire text is there. We read it. We save it as a string in this case. All of you can see my code, right? All of you can see the code?
Yes, sir.
Good. So now this is saved in a string format. A string is nothing but a list, kind of a list. And now if there's a collection and you apply the set on it, essentially set contains only one element once. So essentially it's kind of saying that this is the unique. Now why we are using set and not doing unique? Because the set object is using dictionary. Okay. So the set object essentially is having high memory imprint but low computational imprint because it's order of 1. Anyways, these are basic things of computation, of engineering. This is why set is used, and then it changes into list, and then it is ordered in some format. So this essentially characters is nothing but we are building the vocabulary here, and then we are building the vocab size is nothing but the length of all this vocabulary. So you can say character. So what we are doing here is that we are assuming one important thing. Can someone tell me what is the tokenizer here? We are implicitly assuming one tokenizer. What is the tokenizer here? Anyone? Anyone? What is the tokenizer here? We have the entire text. We're dividing character by character, and then we are building the vocabulary. So what is the tokenizer here? Anyone? You know the answer. I've already told the answer. I've just told it in a different way, using a different language. What are the tokenizers here? What are the tokens here for this text, guys?
So the tokens will be the characters.
Very good. The tokens are the characters. So the tokens are the characters. All of you understood this, guys? Okay, I hope you understood. So the tokens are the characters. Great. So now we are creating a mapping. So we are building an encoding and decoding, which means that the indices essentially we are creating. Okay, so we are creating a mapping from the. So essentially, what it means, if I give the indices, it can give me. So if I give us list of characters, the encoding will be changing it into those indices. And if I give a list of indices, the decoding will be changing into those characters. That is what the encoding and decoding does. Okay, because the output, when I give the output will be in terms of indices, right? Not in terms of characters, right? So that's why it's important. So we are inputting the indices. We are never using the characters anywhere in the model. In the data pre-processing only, we are changing these inputs into this indices, the actual text into indices. So we have these two functions of encoding and decoding. Lambda functions, which are functions, we changing this strings to indices, and decoding is this indices to strings. Okay, now the experimental setup. Again, I have already discussed these things. Now we are doing it in coding wise. So we are selecting a batch size. I have already discussed what a batch is. Now we are also talking about a block size. A block size is what is the context length? What is the text length you will use for predicting the next word? Okay. So that's the block size. We do a random seed. You will now understand why. Now we are doing training and test splits. Here in this case, we build the data loader from scratch. Okay, but they are already inbuilt. This data loader is already there. But here we are doing it from scratch so that you understand that how the data loader is built. So this get batch is nothing but a data loader. Okay, data loader and data like class together. But we are doing it here so that you understand what's happening inside. So we have this entire data. Okay, so we have this text. We encode this text into indices, right? As I said, the whole data is transformed into like 1, 5, 7, 6. Okay, and this index is nothing but based on the vocabulary. So this encode function contains that. Now this entire text is divided into, this is one set. Divided into first 90% text is training, and then rest 10% is validation. That's what it is doing. The first 90% dot till the first 90% is training, and the next 90%, 10% is for validation or testing. Now we are getting the batch. Each batch, as I said, the return is each batch is X and Y. So understand this very carefully what the batch is. So there is a split which is saying that whether it's a train or test, train or val data. Now this is the ID. Okay, so let's say we have this entire batch X, X1, X2, Xn. So what we are doing here is we have a block size, right? We have a block size. So block sizes. So understand what is a batch. A batch is nothing but dividing the entire data set into pieces, which will be used for training, right? So here the pieces will be what? A block and the output Y, right? Simple. Now it's, yeah. So understand this very carefully. So here is the input is data. So since we have the block size, we can only take till less than the block size. right? And this is essentially telling that doing the same thing for all those batches. So many batches. These are vectors, understand this. And Y is also, understand this very carefully. Y is just the next, like here it is I to I plus block size plus 1 for over all I. So it's essentially a block size and it is moving one at a time over this sequence like this. One element at a time. And Y is nothing but the next I plus 1 to like just the next one. The reason you will see, because you will see what's happening here, because there is an attention happening. This is parallelization. Okay. Essentially, it's happening like this. Essentially, it's happening like this one. But here, all the batches are taken together, and it's done in a parallel manner. So in this case, what's happening is, so this is very important. We have 1, 2, 1, 3. So this is divided into two halves. The X is 1, 2, 1 and Y is 2, 1, 3. Why? Because this will create a matrix. 1, 2, 1 and 2, 1, 3. And this matrix is parallelization, can be easily parallelized. And there is something called mask attention, which will make sure that it's focusing on just the next one. Okay. That's what will make sure. So this is very important because this parallelizes the whole thing. Okay. So this is how the X and Y are created. Y is just not 2. Y is this 2, 1, 3. Okay. This is very important. So yeah. So essentially what we are doing is that for 1 we are predicting 2. For 1 and 2 we are predicting 1. The next one. And for 1, 2 and 1 we are predicting 3. So this is how it's happening, like this. For 1, we are predicting next. For 1 and 2, we are predicting the next one. And this is here, in this case, the block size is 4. So that's how the two set of block sizes are created. A matrix will be created, therefore. And this is how the batches are created here. This is, again, an engineering aspect. But essentially, that input is maximum of block size, and output is essentially one of them. Okay. That's how it's trained. But the whole thing is done this matrix wise for easier calculation. So this is X and Y, and this is the input to the model. And now understand carefully for, so this is estimate loss. Yeah, so essentially what it does here is that, just focus on here because we don't have much time. So we have this get batch is X and Y. We run it through a model, which we will be discussing now. We get the logits and the loss, and out of that we take the mean of the losses, and then we train the model. And model.evolve means the model is in evaluation mode, model.train is in model is training mode. That's how the loss is estimated. Okay. Again, these are all the internals of how data loader happens. But it is just spoken out for you guys. But this is the main part, that each batch we get here, because we have the range of eval underscore iters, which is nothing but these batches. Okay. All the batches. And we are getting each batch and we are updating the loss and adding the loss together. Okay. To get the mean of the losses. And we train the model based on that. Okay, so this is clear, guys. The most important learning is this matrix format, guys. This is very important. Okay, where this is the Y and this is the X. Is it clear, guys? Yes or no? Any questions? Okay. So, okay. Yeah. Okay. So now let's understand the GPT model. Okay. So this is very important again. As we have said, there are two important parts. One is data preprocessing, and the model part. So in this baby GPT that we are creating, let's understand what's happening now. So remember, we are importing the indices. So each token here is a character. So we are defining this GPT class which have this following. So what is there is a token underscore embedding table. So what is that? That is very simple. We have each of those indices of X, let's say 1, 2, 3, 1, 3, each of those indices of X or Y. And this index, this is a lookup table. Okay. So nn.embedding is a lookup table. Okay, understand this. There's a lookup table, like there is a kind of infinite dimension, not infinite, but a large dimensional lookup table where each index is a vector. Understand this very carefully. Where each index is a vector. So what they're doing is that using this nn.embedding, they're inputting that vocab size. The end of embedding is nothing but a vocab size, right? It's for all the entire vocabulary. And from that entire vocab size dimension is taken off. Similarly, another such thing is taken off for the positional encoding. Now, positional encoding is what? You're assigning for each position a different vector, right? And token embedding is nothing but you're assigning a vector for each token. So the set of all token is vocab size, and the set of all positions is nothing but a block size, like 1, 2, 3, 4, 5, 6. The length, you can say. The length of all tokens is the vocab size. Understand this very carefully. And the length of all positions is nothing but the block size, because that's the maximum input you will be getting. Did you understand this, guys? Yes or no? Yes. Okay. Okay, so these are okay. So you can see here that different blocks are being created, right? So you create all those different blocks in number of layers. Okay, how many layers are there? So in this case, it's 4 layers. So we have those 4 layers created. Now we have not defined what is a block. So this is what I call, this is what, not I call, but modularization. So when you see a model, guys, this is very important. When you see a model, you modularize it. Okay. What do you mean by modularization? Modularization is breaking up into workable pieces. For example, here there is one token embedding, positional embedding, and then you can see a loop kind of, like it's not the same, but it's kind of, there's a repeatable structure to it. So each block is repeated n times. That's a layer, that many layers. So what you define is you define that block separately and you define the structure together. That's what it's done here. It's modularization. So the block element is defined separately. Okay. And you do it sequentially, so it will be defined separately for modularization purposes. Okay, that block is defined. And then finally, layer normalization and linear layer. That is this. Okay, understand one thing very carefully. The layer normalization is the final layer normalization. It changes the embedding by changing the output is the embedding layer. But the most important thing is the linear head, which is the input embedding, and the output is vocab size. So what does it mean? The output is essentially kind of the dimension of all the vocab size, the probability, to make sure it's a probability. Okay, to make sure it's a probability. So understand what's happening here. So the whole idea is block. The block is the most important part, which we will be discussing later on. The block contains all those transformer layers and everything. But this is the basic GPT structure. We have input text. The text using those embeddings are first changing token embedding by a lookup table of embedding. based on each of these indices. There is a vector for each token has an index. Each token has an index. Each token has an index, and each index has a embedding. Two embeddings. One is token embedding, and one is positional embedding. And those are added. Let's see what they have done. So token embedding it got for those all the IDs for the entire data set, all the positional embedding is done, taken. For all the input indices, the token embedding is taken and positional embedding are taken, as you can see. Okay, you can go into each one of the details later on. Essentially, all these things are, so initially it's T comma C, now it's changed into B comma T comma C. This is important. NumPy automatically does this, automatically adjusts the batch size. Now, why it is this? Understand that each batch has the same block size, okay? Each batch has the same block size. So we do not need to define the positional encoding differently for each batch size. So you can see here T comma C, but each batch may have different embeddings of tokens, right? So B comma T comma C is here and T comma C is here. Now, since each batch has the same positional encoding, what do you do? Instead of defining it multiple times, you add them. So what NumPy will do or Torch will do, automatically it will add it to all the dimensions for the same thing. Okay, so this is a really beautiful aspect of NumPy. And you have to, this makes the computation less. Okay, if you imagine if you do positional encoding for all of them, it will be a lot of work. But here, it is done in that specific specialized optimized way. And it has been done all over and over again. That's why this property has been kept. So finally the X is got, and then all the blocks are being, it's sent through all the blocks. We have not defined the blocks yet, but let's assume block is an abstract class which does all this work. This entire thing is a block. Okay. And then it goes through the output of the block, then it goes to the layer normalization, and then finally logits are being created. Each batch, this T is the, what is this T, guys? Does anyone know what is this T? Think about it, okay? Think about it. Is it a length, the block size, or it is the embedding? Understand the code and understand it later on. It's a homework. So, as I have seen that the entire probabilities of all the vocabularies are created, okay, and then the loss is created. Now you can say where is the probability change? The probability is not done here. Understand, this is a linear output. The probability is already automatically calculated in this cross entropy loss when you do logits and BD. Okay, it's automatically calculated in this cross entropy loss. Just check it once. Okay, that's how we return the logits and loss. And if you remember, in this, the output was logits and loss. Okay, that's why the output here of the baby GPT is logits and loss. All of you understood this, guys? Yes or no? Any questions? Any question? Any doubt? Okay, it's actually very simple if you understand it carefully. Okay, now let's understand the training. We will understand evaluation too, once again, the coding part. So this maximum iterations, evaluation interval. So let's understand this. So we first define the model here. We change it into device, that is GPU or not. And here we check out how many parameters are there in the model, trainable parameters, or rather not just just parameters. And then we define the optimizer. So to do the gradient descent, as I said, there are many ways to optimize the theta. So different ways are there. So gradient descent is there, but currently is Adam optimizer. So we define the Adam optimizer. it's a topic instead of that. So what is the eval interval is doing is essentially every 100 iterations, it is outputting the losses. So that's why it's saying that if the iteration is divided by 100, we estimate the loss. If it estimates every times time, it will be a lot of computation, right? So that's why it doesn't do that. Okay, so now it gets a batch under training mode. So it's model.train. It's already in model.train, and it gets the logits. It defines the optimizer. Okay, when it says that this, it means that it initializes the optimizer. Okay, it forgets what it has done previously. It initializes the optimizer, and then the gradient, the back propagation happens, and then optimizer moves to the next step. Now let's understand the evaluation. So the training is very simple. You already know that, we have discussed it. So essentially it generates. So as you have seen, if you have seen that after X, if you observe it carefully, if you remember input is 1, the next one is input, and that is updated. That is updated, that is attached to the next one. Let's say it's 1, 2, 1, 3. Let's say it's for 1, the output is 2. For then it's attached here, so it's 1, 2, the output is 3. Then attached here, the output is 1 again, let's say. Okay. So this generation process, this generative AI aspect is coded here. So let's understand this. So max new tokens is how many new tokens it will generate. Okay, that's the range of it. It will stop after that. So first input is, it gets a prediction of it's cropped to the block size of the tokens. Okay, last block size of the tokens, and it gets the logits. Okay, because it takes the block size, it gets the logits and the losses. It is not important. The loss is not important here. The logits is important because we take the maximum ID of the logits, and we just focus on the last time step of the logits, and we take the soft max to change into probabilities, and then we sample from the multinomial distribution. Okay. So in this case, as I said, it is not doing the maximum of them, but it is sampling. So sampling means just like you close your eyes and uniformly sample to get a uniform distribution. Similarly, in this case, it's a distribution is there. We sample from the distribution. So the idea is that whichever is the highest probability has a higher probability of coming out. Okay, but it samples essentially. So it samples the ID, which ID among all the IDs, and then it concatenates to the current IDs in the dimension 1. So you now have the answer. This is the length to which it is added, the current length. T is the current length. So essentially, this is nothing but it's adding to it, adding the output to it. Yeah. And then you get this entire, so we essentially decode this entire context to max new tokens. We have the context and we generate this entire thing. Context means the input, and then based on that input, it keeps on generating the next 2000 tokens. Okay, by this above method. So first, the initial context, it is fed in the model. We get the logits. We select the next token. We concatenate to the current logits, the current IDs of the tokens. We input this, get the logits again, get the next one, and get concatenate to the current one, and keep on doing this for the next 2000 tokens. Okay. But understand, it's The context length is essentially the block size. We are not taking more than that. Let's say in this case, if the context length is block size, we will not take this one. We will just take this two. Okay, that's what is done here. That means from the last, we take all the block size, whatever is the current, because as we keep on adding it, the length increases, right? So from the last, we are taking the block size. All of you understood this training and evaluation, guys? Yes or no? Did you understand? Yes or no questions? Yes. Let me again call out your names. Ongona, Orijit, Borshon, Hindal, Kolpita, Konishko, Lucky, Mrityunjay, Rohini, Rupoli, Prutupana, Sanjana, Saurabh, Sritama, Shubhro, Supriyo, Surajit, Shushmita, Shopnoma, and Riti. All of you understood? Any questions? Is there any point you got detached from the entire discussion? Do you want me to repeat? We have 30 minutes, so we have enough time to discuss this. So don't be shy. Okay.
Sir, I wanted to confirm one thing. In
Please,
the
please.
beginning slides, okay, suppose I'm taking a sentence. Yes, this first one. Suppose this masking, this part. So what is happening in parallel is that suppose there is a sentence like, I love ice cream. So first it will take I and try, and I will be the X and love will be the Y. Then in parallel, it will also evaluate I love as X and ice cream as Y. Am I correct? This is
Yeah,
done
exactly.
parallelly.
You're right.
Okay, okay, okay.
So it will do this parallel, yes. So, but yeah, again, this I will be coming this, but you're right. Essentially, it's in the architecture of how it's done. So yeah, this mask.
That is done during the training phase.
Yeah, that is done during the training phase, because it was during evaluation. We are doing this attachment of block size like this. The thing is that for each one of them, we are essentially doing a matrix multiplication. So when we mask it, it is again a matrix multiplication. That's it. Okay. So instead of doing a for loop over all such things, we do two matrix multiplications, and this is essentially what is parallelization. Because matrix multiplication can be easily parallelized by GPUs. How? Because they save it in such a way, they use the memory a lot. They save it in such a way that it can be parallelized. That's how it's done. But the good thing is that the entire process for individual elements is equivalent to a matrix multiplication. And a sparse one, you will see a non-triangular matrix will come up. But that's good. When you have more memory, you can do computation faster. That's what GPU stands for, parallel computation. In CPU, it's sequential computation mostly, for loop sequentially. So yeah. But again, in CPU, the memory imprint is less. You will store less. So that's if you remember more, you can easily capture and do the entire computation together. But if you remember less, you can do sequentially faster. Sequentially faster, not faster. Okay. Any other Rupali, any other doubts? Or any other student, any other doubts?
No, and block size is basically how many words we are taking for a single context. We suppose the block size is 32, then it will try to read 32 words and predict the 33rd.
Exactly.
Okay.
So this 32 length is changing over time. Like it's just it's just shifting. Like it never becomes. It can be 32 or less, but never be over 32.
Yes, right.
Any other question? Okay, so now if you remember that block structure, let's understand this carefully. So each block is this. So we will learn now how to modularize this entire code. Okay, how to modularize? Look into those which are repeating over and over again. So we will see how the first single head attention is. So we have three things which are repeating over and over again: single head, multi head, transformer block, and then using that to build the GPU2 architecture. Okay, so let's see how. See, each multi head is nothing but made up of single heads. We will see that. So linear enumeration is already defined in NN.module. Dropout is already defined. Multi-layer processing is nothing but a linear layer, which is like this. So multi-head attention is there, and you can see multi-head attention is nothing but single head attention multiple times, right? So we need one single head attention. Okay, that means just one of this, and then it is multiples of them together. That's a multi-head attention. Okay, to get the final layer. So we'll see what it means. So we have a single head attention, that is this purple, yellow, and linear, and this entire one. You can see many parallel structures here, right? Many parallel lines. So that's what the multi-head attention is. Because why this? This is because it's like convolution. In convolutional neural networks, there are multiple convolutions, right? So in this case, it is learning multiple relations between the same words or same embeddings. That's why multi-head attention. And they're averaged out using a linear layer, or weighted using a linear layer. That's the whole idea. Just like it's CNN is in CNN, there are multiple convolutions to capture multiple relationships of the image, multiple features of the images. Here, multi-attention is similarly used to capture the multiple relations between words or embeddings. So there is one first single head, the entire single one line, and then using that single one line that is a single head, and then using the single one line to calculate the multi-head, and combine this multi-head to calculate one transformer block, this transformer block, and then using that to create the entire GPT. So we need 4 such classes, modularized classes, right? So let's see that. So this is the single head. Let's understand this very carefully, what's happening here. So some embedding is coming. There's a linear layer, there's a matrix multiplication, there's a mask attention, there's a softmax dropout, matrix multiplication, and then again the linear is essentially multi-head. So let's see. So what is happening? If you remember the key query KQV values, okay? So that's what's happening here. So KQV values is nothing but if there's an embedding, okay, there's a linear layer which is changing into the key, the WK. It is multiplied by that to change into K. So if this I input, it is changed into, by a WK, linear layer is changed into K. So this is that linear layer. Similarly, there is a Q for Q and V. So you can see here that the 3 different, so this dimension calculated so that it made sure that all the dimensions are matching. Okay, the input dimension, the X input dimension, because every layer has different inputs. So yeah, so each of these different embeddings K, Q, V values are created from the input. The X is transformed into this 3 formats: key, query, and value. And then now the matrix multiplication is done to create that attention. Okay, query and key at Q transpose K, or sorry, Q K transpose, if you remember. And all this -2, -1 are done to make sure that they have the same dimension. This is essentially the attention, and then the attention is normalized along all the rows. Okay, with the square root of all the dimension to normalize it. Now a matrix, now a masking is created. If you see, the input is, if you understand this, here is x1, x2, x3, and here's x1, x2, x3, attention. So we want the upper triangular matrix to be 0. So what does it mean? Sorry. And this is what it is. So can someone tell me what this means? Anyone? Mathematically.
So basically, mathematically, it means that x1, x3 value is same as x3, x1.
Sorry, I didn't get
mean,
you. Can you come again?
The value written in row x1 and say column x3 is basically same as x3 row and x1 column.
Yes, but I want you to explain, like, explain me that for x1, x2 is considered, for x1, x2, x3 is considered, and for x1, x2, x3. Yeah. So how is it happening here? So essentially what we mean is that for x2, for when we are predicting x2, we don't have access of x2 and x3. Okay. So that's what it is, the zeros are doing. When we are predicting x2, we don't have access of x2 and x3. When we have x3, we don't have access of x3. When predicting x3, we don't have access of that. So this is what it's doing. Okay. Yes. So this is what it's doing.
Basically, sequentially increasing the length of the blocks or whatever.
No, sequentially hiding the. So when we're doing the matrix multiplication, we don't want the model to learn. When you're using x1, we only want. Sorry, when you're predicting x2, we only want you to have x. Rather, when we are predicting x1, we don't want you to have the knowledge of x2 and x3. And when you're predicting x2, we don't want you to have the knowledge of x3, the future. So essentially, we are hiding the future from the prediction, because so in BERT, this is GPT type, but because you're predicting the future. But in BERT, this is not masked like this, because there we are also letting the future and the present flow together. But in this case, initially, when you're predicting x1, we don't want you to have access of x2 and x3. That's why it's 0 here. When you're predicting x2, we don't want to have access of x3, the future. Got it, guys? This is the whole idea of masking. Yeah, I get. So then this mask matrix is normalized by, so how it is done? Since we are taking a softmax of minus infinity is 0. So we are replacing those, wherever there is 0, we are replacing this minus infinity, so that when you take the softmax of it, it comes out to be 0. Okay, that's why. Very important. And then we have a dropout, and then we have a update of the dropout, like we multiply it, because dropout, that changes the neuron values. Okay, so this is a singular attention, simple. Just the attention, just that whatever happening in the attention. Now the multi-rate attention. all the attention blocks are concatenated together into these attention blocks and with drop. So essentially this single attention at this parameter, so it is defined here, and all of them are concatenated together for parallel computation, and then finally a self linear layer is attached on top of it to get the final output like this, which gives another embedding. Okay, as you can see here. So yeah, you can see all the heads are added around the third. So now we have C cross n heads. So output of one, it's all output is made into this set of heads. Okay, and again this is transformed into BTC by a linear layer. The C times n heads are converted into just C, so that it can go into the next block. So let's create this transformer block. This transformer block is nothing but this entire transformer unit block. So we have this layer normalization. You will see essentially the same thing over and over again. We have this layer normalization. We have defined essentially the first part in definite is defining those layers because those are parameters, and the third part is forward propagation. So we have this layer normalization. We have this, if you remember this architecture. Architecture here. So we have a layer normalization, multi-attention, dropout, layer normalization, which is added here. You can see this is a skip connection if you remember. And again, a skip connection is here. So all these things are done here. We have a layer normalization, we have multi-attention, each are done. As I said, the main idea is here, the first part in the definite, it is about defining the layers because which are parameters, and that their forward is nothing but the forward propagation. Okay. So yeah, I think there's nothing more to discuss here. You can see the skip connection is added here like this. So again, a skip connection is added here like this. So these are all like simple stuff now. Just like this is how you. So I would suggest one exercise, guys. You take any paper out there of any AI if you want to learn how to do this. So I have actually taught this to you, taught this on my newsletter on LinkedIn. If you want, you can check out that. I will show you. But idea is you have to do, if you do it for a few cases, it will be very clear. Okay. If you do for a few cases, it will be very clear that how to transform this into such modularized framework. Yeah, so now if you remember the baby GPT I have shown before, this is the same thing. We are just combining them into all these different blocks to get the final output. So yeah, so this is all about essentially the building LLM from scratch, and it's actually very simple. And I have learned from these two people a lot, and I'm sure you should check out their videos, especially this person's video. He's a gem. He's a gem of person. So you should check out his videos. He has more detailed understanding of just 2 hours tutorial on how a tokenizer is built. So I will show all these links to you right now. Any questions before I move on to show all the links that I can help you out? Okay, so hope you have understood something out of this building LLM from scratch. I would say the most important learning takeaway from today will be about building the data, discussing the deep learning structure and how it is aligned to this large language models. So let me show you a few things. So if you go to Andre Karpati's channel, I hope he has followed. Yeah, he has transformed into 1 million followers. I'm very happy. He has just 17 videos. Just 17 videos. Imagine the amount of information he has. So if you go to this playlist, you will see all these large language models, neural networks, zero to hero. And he is gem of a guy, guys. And he has all this build GPT from scratch, from where I have learned this and taught you guys. So if you want a more better teacher than me, go to him, guys. Okay. All the code are taken from his tutorial. I have just explained you in my own way, in a more simpler way, I would say, and with more time. But if you want the original thing, you should go here. You should actually watch all of his videos, okay? All of his tutorials. You will learn a lot. That I can promise. So I will send this person's link in this. Now there are a few things that I think I have tried to explain a few things so which you can understand. So let me show that to you. So I have this newsletter where I have taught quite a few things, but I have shared this entire thing here with some explanations. One important thing is I actually could explain this whole thing here, what it means. So in a more detailed manner, okay? Like teaching you each of these input sizes and this thing, and how do you actually make these fundamental blocks, how to modularize this, and why this naturally comes up. These things I have already taught in details. And yeah, not only this, I also taught about, this is one example, I also taught another unit architecture from scratch, exactly similarly, with such, essentially I have picked out such regions from the paper, and I have taught you how to build those classes, which classes are very important, and how to modularize those cases. Like so that you, when you think about a model yourself, you can think about how do I build this model from scratch, and how do I modularize this. I have taught a bit about that today, but the thinking needs some more understanding. Another thing that I have taught that is not in this format, but if you go to my GitHub, in Vision Transformers from scratch, I have a tutorial here. Oh, I also published it here in linked on LinkedIn. But if you go here, you can see that I have taken down this entire tutorial of the paper, not tutorial, paper, and broken up into pieces. This is modularization. So you can see how I have modularized each of this aspect. So one singular attention, one multi-thread attention, one NLP head, one embedding, one norm. This is normalization. And this is a transformer block. This is L times. This gives you rise to a transformer encoder. And this entire thing gives you rise to VIT. So we need 1, 2, 3, 4, 5. 5 such blocks. 5 such modularized aspects. And I have taken I have showed you how to read a paper and change it into such blocks. So I expect you guys to take this if you want and learn from it and actually apply it to a new paper. And this will set you up for a good deep learning journey of coding a deep learning model from scratch. Okay, how to modularize it. And this will help you a lot. Okay. So all the best, guys. I hope it was helpful. I will also share my LinkedIn link here if you want. That's it. So thank you all for joining. I hope you have learned a lot from this entire deep learning school, and I hope you have learned a bit from me too. So thank you, guys. Any questions I can help you out with? Else I will dismiss the class. Okay. So thank you. Bye-bye. Have a beautiful... thank you, Kanishka. Thank you. You're welcome.
Thank you